All right, we are recording. Well, hello everybody. Welcome to the third week of climate change education. I wanted to go ahead and introduce Dr. Tony Ingraffea at Cornell. He's a professor emeritus at Cornell, and he's going to be giving a talk on renewable energy in relation to all the things that we've been talking about so far in the last 2 weeks of the course. He's going to give his presentation, and towards the end we will have an opportunity for some feedback, questions that you all can pose. You can post them during the through the Q&A or as a chat directly to me, and I will go ahead and field those questions to Tony directly. If there are some of you that have the ability to raise your hand through the WebEx platform here, I will go ahead and try to get you on the call so that you can ask your question out loud and verbally to him. So, all right. Well, welcome and thanks, Tony. The floor is yours.
Okay, thank you. Good afternoon, everyone. I'd like to begin first by thanking Professor Krasny for inviting me to spend time with you today, and also thank Justin for all the arrangements to make this happen. I'd also like to begin very briefly to tell you why I think I'm qualified to be working with you today. I retired just last year after 37 years at Cornell University, and during that period of time, about 25 years of it, I worked with the oil and gas industry on various aspects of getting oil and gas out of the ground. Ranging from hydraulic fracturing to pipeline safety, drilling, cementing, casing. So I have many decades of experience in the oil and gas industry. Over the last roughly 8 or 9 years, I've been working very hard in the public education arena to inform stakeholders in the public arena about just what is happening with the shale revolution and its impact locally on the environment and globally on climate change. And even more recently, I've begun to do some pretty rigorous study of what the title of the talk is today, Rapid Transition to Renewable Energy. So I'm going to spend the time with you today trying to answer this question. Is a rapid transition to renewable energy possible? And I'm going to say yes. I'm also going to say we don't have a choice, and I'm also going to try to frame why the word rapid is the most important word in that title, because it involves high-level policy. So let's proceed. Here's what I'm going to do. Spend the first few minutes talking about why the transition, which is technically possible, must be rapid in air quotes, and that's to be discussed as we get into the policy aspects of this. I'll then talk about how we began in New York State back in 2009 to ramp up a case study, a leader at the state level for how we might transition one large, very important state in the U.S. to an almost completely renewable energy source for all energy use. Transportation, heating, electricity, industrial, within a few decades. We'll then talk about how that single plan that began in New York State morphed into a national plan and what we now call the Solutions Project, where we address similar issues in all 50 states. We'll spend some time then trying to assess how we are doing, we meaning us, trying to transition to renewable energy, how we're doing on a national scale and how we're doing on an international scale. And then I'll summarize with some points about some of the myths concerning energy security, energy independence, and how we think our plans that we've developed at the national scale are working. So that's what we're going to do. I'll come back to this outline frequently when I'm telling you I'm transitioning from one point to another. So why must this transition be relatively rapid? Here's what we're going to see from a technical point of view, what rapid has to mean. Whether from a policy point of view we get agreement with the technical need for rapid remains to be seen. So I'm on slide 3, which is taken from an article in Science magazine a few years ago, and it's a summary in one slide of our climate past and our climate future. So the horizontal axis is year, starting with the year 1900 up to the year 2070. And the vertical axis is global warming in degrees centigrade. The squiggly line is data. These are recorded temperatures. And as you can see, as you well know, we have achieved now about a 0.7 degree centigrade global temperature rise. And the other things on this chart are a danger zone in orange, starting at 2 degrees centigrade, and what I refer to as the last warning zone, starting at 1.5 degrees centigrade. The 4 solid bars, each of which is in color, are the result of climate scientists working together around the world on the Intergovernmental Panel on Climate Change, using computer models to try to predict our climate future. So each one of those is a scenario. What will happen according to our best, most sophisticated computer models if certain things happen or don't happen? So I want to call your attention first to this purple line, the one I'm pointing to. It's called reference. That's business as usual. That's all the above. That's if we don't do anything different than we are doing now, which is to increase the rate of fossil fuel use. The computer models taken in the aggregate. This is not just one model. It's many models. It's the average of many models. It's Monte Carlo simulation of many models. They say that we're going to get into the danger zone by 2030. I'm pointing to 2030. And we're likely to get into the danger zone by 2042. Pausing for emphasis here. Notice that's not 100 years from now. We might have 100 years of more fossil fuels buried in shale around the world, but we're never going to get to use them. So, of course, these are computer models. They could be wrong. There is always going to be an accuracy the farther out you try to project. The error bar is this vertical purple line, and it says that we might not reach ever that red zone or the orange zone. We might just miss it in the year 2080. Or, on the other hand, our model could be very conservative, and it could be that we're going to get there well before 2042. The red line, is what happens if we had started in 2010 to substantially reduce CO2 emissions. That's the red bar. And it says nothing happens between now and 2040 because of CO2 inertia in the atmosphere. You probably already know about that. The atmosphere responds very slowly to CO2 concentration, and it's currently responding to CO2 concentrations that began anthropogenically at the beginning of the Industrial Revolution. And even if we were to have started in 2010 to do some drastic CO2 emission cutting, we're still going to wind up in the red zone, in the danger zone. The next one is the dark blue one, and that says what happens, according to computer models, if in 2010 we have begun to drastically curtail methane emissions. CH4 is methane, also known as natural gas, and BC is black carbon, soot, like you see from diesel exhaust or what you see from burning some biofuels. The climate responds very quickly to methane because methane is a much more potent greenhouse gas. If we had started 5 years ago curtailing methane emissions and black carbon emissions, the climate would have already responded. And we can see that we would not enter into the last warning zone until 2040, and we would not get into the red zone, the danger zone, until about 2060. So there is a way of slowing down to put a brake on climate change, not by reducing carbon dioxide emissions, but by reducing methane and black carbon emissions. Of course, what we would like to have happen way before 2010, back in the early 90s when we were warned about climate change first, is to curtail all emissions from burning fossil fuels and some biofuels. Curtail carbon dioxide, curtail methane, curtail black carbon. That puts us on the light blue curve. And the computer models all say, well, you know what? There's a really good chance that we never get to 2 degrees centigrade in this century. We are going to continue to rise. There's no doubt about that. We have enough inertia with methane and carbon dioxide in the atmosphere that we are going to get probably into that 1.5 degree range, and that's bad enough. So from a technical point of view, from a science point of view, rapid means in the next decade we have to have done something substantial. From a technical point of view, rapid means within the next decade we have to have done something substantial, lest we wind up on one of these curves. From a policy perspective, I'm going to go to the next slide. From a policy perspective, let me show you a chart that comes out of the United States Department of Energy, Energy Information Agency, and this is the most recent forecast and review of the ways that we use energy in the United States. So let me show you what this means. The most recent report from the Department of Energy looks backwards from 2011 as history, and we can see that as of 2011, here was the way we used energy in the U.S. 26% natural gas, 8% renewables, 8% nuclear, 36% oil, 20% coal. And our Department of Energy, that's part of the Obama administration, is forecasting that business as usual, all the above, will take us here in 2040. I'm looking at the right edge of this graph. And they're right, it's business as usual. Nothing much changes. The federal government anticipates that we will go from 8% renewables to 11% renewables between now and 2040. So there's a contrast for you. The previous slide is scientists saying, if by 2040 we haven't curtailed our use of natural gas, coal, and oil, we're going to be in deep doo-doo. And our government is forecasting that by 2040 we will continue to have used all these fossil fuels in roughly the same proportions we have been using them. Okay, that's the situation. We got to change it. I'm not willing to accept this forecast. So what's the problem? Why do we have to act quickly? Drastic problems require immediate solutions. Air pollution from fossil and biofuels cause millions of premature deaths worldwide annually. Climate change is real. The effects are becoming more evident. Increasing fossil energy use increases pollution, increases global warming, increases energy prices. And higher fossil fuel energy prices do lead to economic, social, and political instabilities. Just look around the world right now. So, how are we going to do about this? Like I said, 5 or 6 years ago, those of us who were fighting the good fight in New York State to try to halt shale gas production from New York State, at the same time realized that we better have something better than shale gas for New York State. So we developed a version of the so-called Jacobson plan. I'll explain what that means, starting in New York State as an example. And it's a starting point. So I'm going to spend the next 15, 20 minutes telling you how we took an idea that first appeared in Scientific American back in 2009, a plan for a sustainable future for the entire Earth to get all energy from wind, water, and sun by 2030, and we mapped that plan by adapting it from the global scale down to the scale of New York State. And we did that for many reasons, which I'm about to describe to you. So we, a group of engineers, scientists, social scientists, celebrities, and of course graduate students, they're the key, got together back in 2010 and started doing research. And by 2012, we had formulated our scientific question: can we map the Jacobson global plan onto New York State? What would it look like? How long would it take to decrease fossil fuels? How much fossil fuel use is there? How much energy in each sector do we have to produce? What kinds of renewables are appropriate for New York State? In which proportions? How much is it going to cost? What kind of impediments do we have? What kind of incentives do we have? And when we were done, we wrote a paper. It appeared in Energy Policy. As you can see, I'm the 13th author out of 13 because I was the oldest, whatever. Anyway, so I'm going to detail to you what's in that paper. And you might want to ask, why did we start with New York State? Well, most of us were in New York State, and we were fighting the good fight, as I said, about trying to halt or prohibit shale gas development in New York State. But New York State is also the 8th largest economy in the world. It has a mix of very dense urban and very non-dense rural environments. We have an example of a very large city, New York City, being the most energy efficient city in the U.S. It's a sufficiently large state that we have spatial scale to work with for interconnected wind power. And it was the state, as I said, where we were fighting that fight, and we wanted to show that the alleged bridge fuel methane was, in fact, a gangplank, but we had a better idea. We didn't need to bridge over fossil fuels with a fossil fuel to get to a renewable future. We were already starting. We don't need a bridge. We just need to accelerate down the highway we're already on. Pardon the mixing of metaphors. So first we have to decide what energy sources we weren't going to include in our plan, and obviously we're not going to include natural gas. It's not a part of our plan for the reasons that I indicate on this slide, and I have been involved in many publications, peer-reviewed journal publications on the issue of shale gas, methane emissions, and climate change. We had a number of people with expertise in that area, so we feel very confident that natural gas should not be a part of our ongoing energy policy, despite the EPA Clean Energy Plan, or Clean Power Plan, calling for an increased use of methane for electricity generation. We completely disagree with that. Mostly because methane is, as I said before, a very strong, potent greenhouse gas, and it's the only decelerator we have over the next few decades to slow down climate change. It's the only one we have. Why not clean coal with carbon capture? Here are 4 good reasons why not. Clean coal concept is pretty much put to rest. It's an oxymoron. There ain't no such thing. It's a wrong way to proceed with your tax dollars. Why not more nuclear? Here are 5 good reasons. And the last one I think is most telling in terms of rapidity, this idea we have to do something in the next decade. Even if we were to overcome the first 4 problems with nuclear power, it's too late for nuclear power to have any substantial impact in our fight against climate change over the next decade or 2. It just takes too long to build, to license, to ensure a nuclear power plant, and we need quite a few of them. All right, we also had to overcome some myths about New York State. Myth number 1 is it's not windy enough in New York State to make wind energy practical. Well, that's untrue. I'll show you in a few minutes that there is a substantial deployment already of wind resources, and the rate at which they're being deployed in New York is rapidly rising. And this is a map that shows you the distribution of capacity factors for wind energy. The colors just mean if you put a wind turbine in a certain location at a certain color, the percentage tells you how much of the nameplate energy capability of that wind turbine you're likely to get on average over a year. And anything more than 30%, actually anything more than 25% is considered pretty good for onshore. And as you can notice, New York has substantial offshore capabilities, Lake Erie, Lake Ontario, and the Atlantic Ocean. Next myth, it's not sunny enough in New York State to make solar energy practical. Well, I happen to have 8 kilowatts of PV on the roof of my house, and I don't pay any electricity bills. I also don't have a gas line coming in my house, so I don't have any gas bill either. So there's plenty of sunlight in New York State to make solar a very significant part of the renewable portfolio in New York State. So then we did the calculations. We had to figure out how much energy of each type for each source, for each demand, I should say. Transportation, home heating, industrial heating, feedstocks, industrial use. How much energy is currently being used in New York State? Because we have to replace most of that, but not all of it. And we then have to figure out, given that we're not going to use nuclear, we're not going to use gas, we're not going to use coal, what portion of each type of renewable is most appropriate for New York State? And this is where we wound up. So this is after 3 years of research with a lot of grad student work. You'll see that we have onshore wind, offshore wind, wave devices, geothermal plants, hydroelectric plants, tidal turbines, residential roof PV systems, commercial and governmental roof PV systems, and commercial PV systems. And in the right column, you'll see the number of each type that we need. So here's the first time you're going to realize, well, something you already know. The numbers are large. To replace fossil fuels with renewables is a really big task. So that's message number one. This is what we'd have to do in New York State. Then the questions arise, how the hell are we going to do it? What are the incentives to do it? What's stopping us from doing it? How much is it going to cost? How quickly can we get the job done in New York State? So first thing we note is that if we convert entirely to a renewable, that is sunlight, water, wind, energy source for all energy uses in New York, we don't need as much energy, because those forms of energy directly create electricity. And electricity is a much more efficient use of energy than burning fossil fuels, by roughly on average 30%. So you automatically get the efficiency gain without even trying to reduce our consumption, which obviously we're also going to do by conservation and efficiency. Just by going from burning fossil fuels to running things on electric, like your car and heating your home, we gain about a 35–36% efficiency. That means we don't need as much energy for New York State in 2030 than we have now. Here are the various forms of efficiency gains at the home level. I have all these in my house. I hope you have them in yours. We also can directly start to count the health benefits of switching away from fossil fuels, because this takes us into the economic regime. What's the trade-off? If we have to invest billions, hundreds of billions of dollars in transforming New York from largely fossil fuels to almost exclusively renewables, what do the economics look like? And part of the economic picture is how much savings we have. $33 billion a year we project in death and morbidity caused by fossil fuel generated air pollution. So that works out to a very substantial amount of money per person and over the state and over the next 20–30 years. In fact, one can make the argument that the savings alone in healthcare and death would pay for the transition in about 8 years. That's a hypothetical calculation and it's pie in the sky, but it's real. All right, jobs. We often hear that we need to stay on fossil fuels because they keep people employed. Well, you well know that there are plenty of jobs available in the renewable energy field. Here's some statistics that say for the average number of jobs in the U.S. per $1 million spent on energy production, 3.7 for jobs for fossil fuel, 9.5 for wind, 9.7 for solar. So the job intensity is better for renewables than it is for fossil fuels. There's a trade-off. The energy intensity is better for fossil fuels, but the job intensity is better for renewables. Total job creation in New York State, here are the numbers. We won't spend a lot of time. It's just that they're up in you have construction jobs, nearly 250,000 over the next 30 years, and then operations jobs, people who have to stay working in these various plants and forms of renewable energy, over 100,000. Forever. How much area of New York State would have to be taken up? That's an argument we hear all the time. Not much. Bottom line, total space of all New York State space, not including offshore, this is just onshore, 1.3% of the state would be taken up. And since upstate New York is largely empty, that's no big deal. What's the cost? We estimated 2 years ago about $485 billion over the period 2013 to 2050, roughly 35 years. So $10 or $12 billion a year, $15 billion a year. There's a certain former mayor of New York City who could probably come up with that out of his own pocket. And as we'll talk about later what this is compared to, that looks like a big number. The millions of rooftop PV systems look like big numbers. But I warn you, there are some other big numbers involved in fossil fuels that we have to compare those big numbers to. For example, New York State was facing, a year ago, 50,000 shale gas wells. That's the estimated number of shale gas wells that would have been drilled in New York State to get its shale gas. Those 50,000 shale gas wells, just to drill them, is $250 billion. And that $250 billion does not come out of Exxon's bank account. It comes out of ratepayers. Would have come out of the people of New York State's bank accounts to pay for those 50,000 shale gas wells. And when you think of it, what choice do we really have when the economics and climate change is going to dominate all costs over the next 20 or 30 years? We also compute and predict that going to renewables stabilizes and ultimately reduces energy costs compared to fossil fuels. As the fossil fuel supply dwindles and as the demand for it continues to rise, its cost will go up. Since the cost of renewables is fundamentally not based on material, sunlight is free, wind is free, water is largely free when it's falling over Niagara Falls, there are no material costs. We don't have to go out and drill wells. We don't have to pay for gas. We don't have to pay for oil. So once you have the infrastructure in place to produce and transmit electricity from wind, water, and solar, those sunk costs are basically constant. So here's our prediction of the economics in the future. The annual energy, health, and climate cost savings per person in New York State by 2050 will be $5,000. The annual energy cost savings per person would be $2,100. And if you just want to look at a graph, this is what we anticipate. Again, horizontal axis is year. Vertical axis is the source of energy. Back in 2000, about 5% of all the energy use in New York was from renewables. What we'd like to do is get to roughly 80% renewables by 2030 and 100% by 2050. And the colors show you the various proportions for the plan for New York State. So there it was. We published a paper and said, folks, get serious. This is a big problem. For New York State, optimizing the various renewable sources, here's what we think the mix should look like. Here's the amount of energy we predict we're going to need. Here's how long it's going to take us to do it. Here are the political impediments. Here are the sociological impediments. Here are the legal impediments. Here are the economical impediments. Let's get to work on the impediments, get the job done because we don't have a choice. And when we were done with New York State, we said, why stop there? Let's take the plan nationally. What would that template that we developed in New York State look like if we took it out to California? A much larger state and area, larger population, totally different climate. We expect that we'd have a different renewable energy mix. And so we got to work. We meaning some of the people you see in this photograph. Here's Mark Jacobson, the professor at Stanford that started all this. Bob Howarth, my colleague at Cornell, Dr. Jeanette Barth, my colleague here in New York State. Here are some of the celebrities that got involved. It takes money to do these studies, and we're not getting any money from Exxon to do them. So the next thing we did is wrote a paper that said, what would it look like in California? And by this time, I had moved up to third author, not because I got any younger. And the picture for California looks different. In fact, you're all from many different states, so I challenge you tonight, go online to the Solutions Project, www.thesolutionsproject.org, and you'll see a map of the United States come up. You click on your state, and you will get an in-depth evaluation of all the work that our graduate students did, looking at your state in particular, and telling you from an optimal point of view, from a technological optimal point of view, what mix of renewables is appropriate for your state. And you'll see the different one for each state. There's a lot of work behind these calculations. This website does not show you all the political solutions, all the sociological solutions. No, these are technical solutions with a highlight of the kinds of problems each state presents from the point of view of regulations and law. So try it tonight. See what your state looks like, what it's going to take. Big numbers. I warn you again, big numbers. Don't be surprised. Okay, more numbers coming your way. If we had started with a solutions project back in 2010, and we had gotten the governors and the legislatures of all the states to agree to get on to this plan, and if we had found a way of getting all that Wall Street money diverted from drilling holes in the ground to doing things with sun, wind, and water, we'd be farther along than we are today. But we are pretty far along. Again, we don't need a bridge over one fossil fuel with another fossil fuel, which makes no sense, by the way, conceptually, to get to some place 50 or 60 years from now, which is renewable. We don't have 50 or 60 years. We don't need a bridge. We just need to move faster down the highway we're already on. So let's take a look at that highway. Where are we in terms of renewable energy in the U.S. right now? And where are we globally? Where were we 10 years ago? Where are we today? What is the rate of change? What can we reasonably expect to see over the next decade or two? All right, so let's start in the U.S. This is a busy slide, but if you've never seen it, you should download it and study it. It's a picture, starting on the left, of the various energy sources, starting with solar and going all the way down to petroleum, of the various sources of energy used in the U.S. today, actually in 2013. The U.S. consumed a little bit short of 100 quadrillion British thermal units of energy for all end uses. So you can follow the roads and go across and see where all that energy went. So of all these energy forms, 38% of it went to produce electricity. 11% of it went into residential use, 8% to commercial use, 24% to industrial use, 27% to transportation, and we wasted 59% of our energy. Wasted. Never got used. Wow, that's dumb. Over 50% of the energy that we produced never got end used. It was rejected as waste heat or friction or of some other sort of dissipation. Got to be a better way to do this. There is. It's one we've just been talking about. So we need to figure out how to get off of petroleum, how to get off of coal, how to get off of natural gas, ramp up all these, and at the same time increase electricity consumption so that we can run our cars, heat our homes with electricity, and reduce misuse of energy, loss of energy, waste of energy. So you notice when you're driving in your car how hot the engine gets? That's waste heat. Your car is only about 25% efficient. Roughly 25% of the energy in your gas tank doesn't get used to move your car. If your car has batteries, about 85% of the energy in those batteries goes to move your car. All right, so that's the picture of where we are today. Another way of looking at the picture is move it forward. If we were to map this 2013 map, which is the most recent available, by the way, into 2014, what would it look like? I don't know, but I'll give you some hints. Let's take a look at new U.S. electric generating capacity additions over the last 3 years. So we're going to go backwards here. Electricity generation is 38%, roughly 38% of all energy use in the United States. For all the new capacity of electrical generation, where did it come from? Well, last year, 32% of all new electric generation capacity came from solar. 23% came from wind. 42% came from burning methane. Okay. So you look back to 2012, solar was small. 2013, it got bigger. 2014 got bigger again. Wind varies depending upon incentives from the federal government, which wax and wane, unfortunately. It's good news to see that methane started off growing, and now it's starting to decrease. Another way of looking at things is to ask the question, let's look back over the last 10 years and look at solar electricity generation, photovoltaic, PV installations in the United States. This is U.S. only. By segment. By segment, I mean that used solely in residences, non-residential, that would be commercial and government buildings, and utility scale. So let's look at utility scale. You'll notice back in 2005, it was virtually zero. None of your public utilities were producing electricity using the sun. By 2014, substantial change. Apparently substantial change. Residential, again, virtually zero, 2005, and starting to increase what engineers call exponentially. But here are some caveats. The vertical axis here is megawatts. That's a measure of how much electricity is generated by what's on the roof with solar panels. 1,000 megawatts, a gigawatt, is about the output of one large nuclear power plant. In other words, you've got to divide these numbers by 1,000, and that'll tell you roughly how many equivalent nuclear power plants we've built with PV over the last 10 years. But it's even worse. Sun doesn't always shine. So we have what's called a capacity factor. What is, on average, the percentage of how much power could be generated by PV that you actually get? And that's only about 15 or 20%. So first you have to divide by 1,000, then you have to multiply by about 0.2. So in 2014, collectively, over the entire United States, taking into account all of the solar panels that were built and deployed, we created what is the equivalent of about one nuclear power plant. And that is about 1/1,000th of the total U.S. electricity generation. The United States generates about 1,000 gigawatts of electricity every year. So, okay, these curves look good, but boy, we have a long way to go. I'm not saying that to be depressing. I'm saying that to be suggestive. We have a long way to go. Look at the track record we have over 10 years. Fantastic. If we keep up this rate of growth, those of you who know about mortgages know that compound interest really helps. If you're doubling every 3 or 4 years, it doesn't take you a long time before you've gotten some fantastic results. Let's look at the world scale. Again, this is photovoltaic, PV, solar panels, over world scale. Again, back in 2000, this is now 15 years ago, virtually nil. 13 years later, 138 times increase. So in 2013, the total equivalent photovoltaic electricity generation in the world was equal to about 25 nuclear power plants. But that's a factor of 60 increase in 10 years. If we keep that rate of increase up, factor of 60 in 10 years, in fact, this is exponential, so we could expect more. That 25 nuclear power plants now becomes 1,500 nuclear power plants. Now we've made a huge dent in the world electricity demand. So the message here is we came from virtually nothing about 10, 15 years ago. We're on exponential growth curves in photovoltaics nationally and internationally. If we keep up the rate of increase, we can expect that in 10 years, that's the window of opportunity we have. In 10 years, we're going to have very substantial photovoltaic electricity generation capability nationally and internationally. A big bite out of fossil fuels has been taken. We can afford to downgrade, slow down, diminish fossil fuel use as we substitute photovoltaics. Let's go to wind. Again, I'm going to give you a before and after. Here's a map of the U.S., 2004. The colors for each state that are colored tell you how many megawatts of wind capacity was available in those states in 2004. Those of you who have political bents might notice that there's some similarity, not perfect, but some similarity between a political map and a wind generation map, with some exceptions. Look at Texas. Second only to California in 2004. But in 2004, we were only generating about 6 gigawatts of wind. Again, that's equivalent to roughly 6 nuclear power plants, But we have that capacity factor again. Now, the capacity factor for wind is higher than it is for sun. It's roughly 25–30% on average across the U.S. So let's see, in 2004, we had wind power equivalent to about 2 nuclear power plants. And remember, that 2 nuclear power plants is, as compared to 1,000, right? We have roughly 1,000 gigawatts of electricity generation demand in the U.S., and of that 1,000, here we have 2. That's 2004. Fast forward, 2014. We go from 6 megawatts to 65 megawatts, factor 10 in 10 years. Right? That's a factor of 100, 10 more years. Factor of 1,000, 10 more years after that, if we can keep up the rate of growth. So by 2014, we had wind power equivalent to about 20 nuclear power plants. That's 2%. And that's a factor of 10 increase in 10 years. 2% of total energy demand in the U.S. coming from wind. And look at what's happening. We're filling out the map. Again, Texas #1, California #2. But even places like New York, significant. Iowa, very high. So, message here, again, we came from virtually nowhere. In 10 years, we're somewhere. More importantly, the rate of growth is exponential. If we increase by a factor of 10 in 10 years, exponential means we're going to increase by more than a factor of 10 in the next 10 years if we just keep up the energy level, personal energy level, political energy level, economic energy level, to keep doing what we've been doing. We stand a chance of having very significant bite taken out of fossil fuels in a decade. Looking at the world view for wind, this is 17 years of view. Again, if you go back to 1997, again, this is megawatts. So back then we had roughly 7.6 times 0.3, 2.5 nuclear power plant equivalents. By the time we get to 2014, we have equivalent to about 110 nuclear power plants worldwide coming from wind. Same story, exponential growth. We need to keep up everything I just said, economic pressure, political pressure, remove the sociological obstacles. We don't have a choice because, as I told you on the first 2 slides, the climate is speaking back to us. It's screaming back at us. We kicked it around for 150 years and abused it. You did, I did. We demanded fossil fuels. And now we're paying the piper. And now the climate's yelling back at us, stop, 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 help me, help me, help me. This is the way we help it. So, summary. I'm going to show you this slide again. This is going back to New York State, looking at all the renewable energy technologies we decided were optimal for New York State. Here are the numbers. 11,000 offshore wind turbines. 8 million residential PV systems. Those are huge numbers. And when we show these numbers to people in the legislature, they laugh and they say, oh, you're kidding, never be done. But when the industry comes along, the oil and gas industry comes along and says, hey, we're going to build 50 to 100,000 Marcellus shale and Utica gas wells in your state, nobody blinks an eye. Those are big numbers. 50 to 100,000 wells, 8,000 to 16,000 pad locations, each of which takes 5 to 10 acres, mostly of tree removal, 500 to 1,000 compressor stations, thousands of miles of new pipelines. This is just in New York State. Thousands of incidents of well water contamination. We will increase New York's contribution to global warming. We continue illness and morbidity from fossil fuel pollution. This is the one I like to use as a metric. And if we were to drill those 50,000 shale gas wells in New York State, which hopefully will now never happen, we would have sequestered forever twice the tonnage of steel currently used by the United States Navy. Drilling those wells and putting steel casing down those wells would require twice the amount of steel currently deployed by the United States Navy. Stuff it underground, never to come back up, non-recyclable. So people look at these numbers and gasp. Why don't they gasp at these? We're preconditioned to accept what the fossil fuel industry says is necessary, and we balk when we're shown the numbers of what really is necessary from a climate change point of view. Don't get balked. Finally, energy security and independence. Who owns the sun? Not Saudi Arabia and not Exxon. Who owns the water? Who owns the wind? We do. Everybody does. So if you want an energy source, or energy sources that nobody has to fight over, no country needs to fight over wind, water, and sun because they own their own piece of the action. It's rather obvious, but you don't hear a president saying that. You don't hear people in Congress saying it. If you want true energy security and independence, use energy sources that you don't have to fight over because everybody owns them as much as they want of them. Sorry to be simplistic here, but that's the way I look at it. We own the wind, we own the sun, we own the water. They make everybody, every country, energy secure and independent if they have the means to use them. Give the people of Ukraine the means to use wind, water, and sun, and they can tell Putin to go to hell. So, pardon my French. In summary, we need to switch to electricity, electrified transportation, electrified commercial and domestic heating. Those are the low-hanging fruits. We get greater efficiencies in doing that, which means we lower the total energy consumption, for example, in New York State by 37%. It's going to vary from state to state, country to country, but we do get greater efficiency by moving away from burning fossil fuels to using electricity. In each state, each country, each region, choose the most environmentally benign generation technologies. Most importantly, because of that rapidity, we need to be doing something now, and we need to be doing a tremendous amount of work worldwide over the next decade. We have to rely on technologies that are commercially available today, and we have them. Ask GE how many different versions of wind turbines they've gone through just in the last 5 years. Look at the photovoltaic industry and how quickly it's reducing cost and increasing capacity. Use a variety of energy storage techniques and approaches for balancing demand to production. I'm sure you've studied some of those in the last few weeks in your course. Use hydrogen generated from excess electricity production for industrial process energy. Our plan, the solutions plan, it's cost effective because look what it saves. It saves all those health costs, saves all those costs of debt, saves you in climate cost savings. Just in New York State alone, $36 billion per year over the next 14 years, our estimate, conservative. We will create a large number of net new jobs. We don't have to import guys, yes, it's just guys, from Texas or Oklahoma into New York to drill wells and then go home. We create jobs in California, in New York, in Wyoming, in Colorado, in Texas, wherever we're doing it. Stabilize energy prices, greatly improve energy security, reduce energy prices on a time scale of 10 or more years into the future. Again, nobody owns the sun, wind, and water. My fondest hope is that Rex Tillerson, the CEO of Exxon, gets up at the next shareholders meeting and says, we're the biggest fossil fuel company in the galaxy. We got all the brains, we got the smartest people, the best engineers, the best scientists, the best chemists. We're transforming ourselves starting today into a renewable energy company. We don't want to close up shop in 10 years when all the oil and gas is gone, and we don't want to continue to contribute to what people of the world ask us to do. Remember, we're not guilty here. We are already doing what everybody asked us to do, produce fossil fuels. But now they're telling us, stop producing fossil fuels. Start producing renewables. We don't have to lay anybody off at Exxon. That's my dream. And we can hugely decrease death and morbidity from air pollution and greenhouse gas emissions if we do what I just described. So, in conclusion, peace to you all. Thank you very much for your attention. I think I left about 10 or 12 minutes for Q&A. Thank you for attending and participating. Looking forward to your questions.
Wow, thanks, Tony, for such a great presentation. What you presented was both scary and hopeful. And I have a couple questions, and I think Marianne has posted a question, and if others have questions, please go ahead and submit it through the chat. I think the first question Marianne asked was, how is your team working with other big consumers like China and Europe?
Great question. Directly, in terms of information exchange, I'm not aware of any direct connection with China, but Mark Jacobson and others on our team are frequently having personal interchanges, visits to countries in Europe and Asia, other than China. I don't know anything about China in our team, but literally daily we have information exchanges, data exchanges. We're constantly getting bombarded with questions from all around the world about our plans, how we did them, how those plans could be mapped on to different countries, different provinces. So the Solutions Project, again, was born in upstate New York. It morphed into a national organization. It's now trying to become an international organization, and there are probably people in each state that every person on this webinar is coming from, where they can contact somebody from the Solutions Project. If they want to know who to contact, they can get in touch with me by email, and I'll point them to the right people.
Thank you. So I have a question. So based on the current rate of growth and the capacity for solar, wind, and other sources, will we follow the light blue line that you described in the projection?
Oh boy. Hold on. I can't see how to go back quickly. I'm not sure, and let me tell you why. I would hope so, but I'm not sure. I can't answer in the affirmative for sure, because this light blue line, again, is the result of the average of a number of computer simulations using different climate models from different scientists and laboratories around the world, rolled into Monte Carlo simulations with probabilities associated.
Sure.
I don't know exactly what went into those scenarios. I would have to go back and read, or you would have to go back, or anybody else that's listening would have to go back and read a number of papers from those various labs to figure out for each simulation done by each laboratory around the world what rate of change of methane emissions and black carbon emissions went into their simulation, and then more fundamentally, how that rate of change, rate of decrease of methane emissions came about as a result of substitution of renewable energies for fossil fuels. You'll note that the title of this paper, looking at the bottom of the screen, is Simultaneously Mitigating Near-Term Climate Change and Improving Human Health and Food Security. So the scientists that wrote this paper, there's a whole team of them from around the world, had to take into account all the things I've been talking about. You don't just turn off fossil fuels and let people freeze in the dark. You got to make sure that you can still have them growing their food, distributing their food, heating their homes, getting light, getting transportation by gradual transition. So they've taken that into account in all these models. But the exact details of what went into each model, I can't begin to describe here. That would take a lot of work on the part of anybody wanting to dig that deeply, and I assure you it'll be very rewarding, because then you can play your own games of, hey, I wouldn't have presumed that, I would have done this. And certainly it's not going to be at the level of detail of an individual state. At best, they probably looked at regions. They looked at North America, South America, Asia and the Pacific, Africa and the Middle East, and they can't parse down to the level of a county or a state when they're doing simulations like this. But great question, the kind of question that a faculty member poses to a potential PhD student.
I got another one, and I think this relates perhaps to the group itself in terms of the environmental educators and their role in trying to push this, advocate and educate people in a way that offers this as a viable solution, right? And I guess what the question is what kind of level of investment in education and retraining will we at state and national level need to make to be able to do this? Because I know that there's, you know, part of that capacity is the human capacity, right? And in terms of, you know, we've got environmental educators on the call listening, watching this webinar, and I want to know what you think their role is going to be in this energy revolution.
Wonderful question. And since I'm one of you, I'm an environmental educator. First and foremost, tell the truth. You know, tell it to the wind. Pardon the pun, tell it to everybody, but most importantly, tell it to your students. We need to be able to discern when we're reading bullshit. And unfortunately, there's a lot of it in Congress. There was a lot of it today. There was testimony before the House Committee on Science and Technology given by representatives of the oil and gas industry that was, to be polite, tomfoolery. So one needs to develop the ability to discern when what you're reading really is the best available science, engineering, and technology. So that's first and foremost. Become a competent purveyor of data and information generated by the science and engineering community around the world with respect to climate change and renewables. Inform your students of the scope of the problem. This is not trivial. This is not an overnight fix. I tried to emphasize that. Hopefully I didn't overemphasize it by depressing everybody. But we have to build and change a huge energy infrastructure. Okay? Our energy grid, our electricity grid needs to be reformed. Everybody knows that. We need, quote, smart grid. I'll give you a specific example of the kind of problems that your students are going to go out and face. They're going to graduate from your institutions. They're going to go to work for renewable energy companies. They're going to go to work for corporations that want to start using more renewable energy. And here are the kind of problems they're going to face, just from the point of view of the energy grid. Here I am in the most enlightened county in the galaxy, Tompkins County, upstate New York, Cornell University. We're building solar panels over the place. We got community-scale wind farms. Cornell University gets huge grants from the state of New York to build solar farms. So they try to go out on the 10 or 20 acres that they own here, there, and everywhere in the county and get permits to build their solar farms. And of course, they have to come into conflict, unfortunately, with the Public Utility Commission and the local electricity supplier, the local utility. And the local utility says, hey, our electric lines out there near that field can't accept all the electricity you're going to generate, so you can't build it there. Cornell goes back and says, where can we build? And they said, well, you can build near our substations. Cornell doesn't own any land near the substations. Okay, now what? The Public Utility Commission now has to get involved, hypothetically, and tell the utility, you need to upgrade your power lines in that county so that that university and that community can start deploying more and more wind and solar. So we can build these things, but we might not be able to connect them to the grid. The analogy here is the fossil fuel industry now is drilling 40,000 new gas and oil wells a year, and until they have pipelines, they can't get their product to market. So there's the analogy. They want to build more pipelines to get more fossil fuels to the market. We need more pipelines in the form of high-capacity grid lines so that we can put our wind and solar farms in places where we have permission and where we have environmental best location to build them. So the point is, you got to be talking to your students about those kinds of problems that they're going to see. They're not all technical problems. Some of them are regulatory problems. Some of them are legal problems. Some of them are environmental problems. So you have to be giving them a cross-disciplinary view, if not a cross-disciplinary education itself, a cross-disciplinary and interdisciplinary view of all the kinds of factors and all the kinds of entities with which they're going to have to interact. So that's a long answer to a really important short question, and touches the surface. Those are the things I talk about when I get out in the public and I get the same question: what can we do? You told us there's a problem. You told us here are potential solutions. How do we get there? You start with what you can control. You start in your own home, start in your own car, work outwards from there. Next is the business you're working for. Next is the business you're going to start to take advantage of these opportunities. Next is interacting through writing op-eds to your newspaper so that people in the legislature, at the county level, at the state level, see the will of the people. Enough said there.
Well, thank you so much. I just wanted to say that I did not think and I can't speak for everybody, but I did not think that your presentation was entirely depressing. Actually, it was more hopeful because I see a clear path. And I think that's one of the real important things that you contribute with your group, is that there is a clear path.
Yep, towards, scoot on down that highway. Just speed up.
Really.
Don't need a bridge. Don't need a bridge.
Well, I think that's one of the things, is that so much of the discourse is the problem, and the problem obviously is what helps motivate action, but without that clear path, right, then what do we do? That question always ends up coming up. But I think that there is hope here, and looking at that exponential growth rate, it makes me think that it would be a really good business investment.
That's right. I'm hoping that the teachers. I'm a teacher too. I'm telling my friends and my students, man, get into business. You want a sure thing? Tell me, show me a surer thing than getting into the renewable energy business in some way, means, or form. Honestly, today there is no. Yeah,
the rate of growth is that's a great return on investment, I think.
Exactly.
So. Well, I think we're out of time, and I just, again, wanted to thank you for taking the time to present your work and your thoughts, and I know that I got a lot out of it, and I'm sure everybody else did. And thanks, everybody, for attending.
Yeah, thank you all. Honor and a pleasure to be with you.
All right, well, have a great day.
Thank you.